All right, Algebra 2 students. So 8.1, we talked about confidence intervals, but we talked about them generally. So now we're going to talk about creating confidence intervals for population proportions, and we're going to get more specific. So if we go back to the sampling distribution of p hat, what do we know about the shape? It's a distribution of all these different p hats. We know that we'll have a normal shape if NP is greater than or equal to 10 and N1 minus P is greater than or equal to 10. We know that the center mu of P hat is P, our population proportion. And the spread, that standard deviation of P hat, is P1 minus P over square root of N, all of that. We've seen all of this before, and there's nothing new. It's just remembering. So the three conditions necessary for constructing confidence intervals are that random, normal, and independent. We need to have a random sample, or random assignment. It'll be normal if we have that normal condition from above, that NP N1 minus P greater than or equal to 10, and we need an independent sample. But most of the time we won't have an independent sample. Most of the time we need to use that 10% condition. Our sample cannot exceed 10% of our population. So in each of the following settings, check whether the conditions for calculating a confidence interval for the population proportion P are met. How would you change the setting if the conditions aren't met? So an AP statistics class at a large high school conducts a survey. They ask the first 100 students to arrive at school one morning whether or not they slept in 8 hours the night before. Only 17 students said yes. Well, does it meet the random condition? Is this a random sample? That first 100 students is not a random sample, so we'd have to give everybody a number and pick the first 100 numbers at random. If we check the normal condition, n is 100 and p is 17 out of 100, so 0.17. So np and n times 1 minus p are 100 times 0.17, so 17, and n times 1 minus p is 100 times 0.83, so 83, and both of those are greater than or equal to 10. So the normal condition is satisfied. And then independent, well, if we ask the first 100 people, we don't know if that's independent or not, because we don't know if we ask them one at a time and if any of those first answers could affect the other ones. But I don't see any issues. We can check the 10% condition. 100 is less than 10% of all students at that large high school. We said it was large, so we're assuming that it's large enough population. So constructing a confidence interval for p hat. So remember, we have our statistic. So in this case, for proportions, our statistic is p hat. We have our critical value, which we'll talk about in a second, and then we have our standard deviation of the statistic. So standard deviation sigma p hat, which was p1 minus p over n all square rooted. So when we built a 95% confidence interval, we're trying to remember what our critical value was. So remember, for 95% confidence, that was 2 standard deviations. So that's why we said 2 from our empirical rule. But now we're going to be a little more specific in how we find our critical values. So at 90% confidence, we're going to say we're within 90% of the data is within some sort of standard deviation. Remember those z-scores. So what we're going to use is our standard normal, mu equals 0, sigma equals 1, and we're looking for that middle 90%. So if we think about it, what's left in the tails, there's 10% for both tail, so there's 5% within here and 5% within here. So if we're doing the inverse norm to find our z from chapter 2, we would use 95%, 90 and that 5%, so 0.95, area to the left, 0, 1. This will give us our z. So 1.645. With 95%, remember we assumed that it was 2. Well, it's not quite 2. If we have 95% of the data, that means there's 5 for the tails. So that means that there's 0.025 over here and 0.025 over here to add up to that 100%. So when we do our inverse norm, we're using 0.975, 0 and 1. So 1.96 if I were to round. Now that's very close to 2, but it's not 2. So I've kind of been lying this whole year, but when we say the empirical rule, 95% of the data, it's about 95% of the data within 2 standard deviations. And if we do 99 real quickly, then that means there's 1% in each tail, so 0.005 in each tail. So we want our z-score, and we'll use 0.995. So 2.58. So Mr. Donahue wants to estimate the proportion of students who believe that school should have been called off because of weather. He called a simple random sample of 32 students, and 19 believe that the school should have been called off because of weather. Create a 95% confidence interval for the true proportion of students who believe that school should have been called off because of weather. So if we name the procedure, we're going to do a 1 sample z confidence interval. For the proportion of students who believe that school should be called off for weather. We have to check our conditions. We had an SRS, so it was a simple random sample, so it was random. Normally we have to check NP and N1 minus P. Well, N was 32, and P was 19 out of 32. And I'm just going to tell you that they both are greater than or equal to 10. So the sampling distribution is approximately normal. And then independence, we need to check the 10% condition. So 32 students needs to be less than 10% of all students at Franklin Heights. Well, it is. So that meets our independence condition. And then our results. So we have our P hat, which was 19 out of 32. Plus or minus, we have our 95% confidence interval. So remember, we just found that z star that goes with that, and it was 1.96. Times our standard deviation. So 19 out of 32 was our P hat. 1 minus 19 out of 32 over N, which was 32, all square rooted. So there's our two bounds, 0.42 and 0.76. Now I could have made those decimals if I wanted to make it a little easier to calculate, but I didn't feel like it. And now we need to interpret. We are 95% confident that the interval from 0.42 to 0.76 captures the true proportion of students who believe the school should have been called off because of weather. Now we could use our calculator to find that confidence interval as well. So we go to Menu, Statistics, Confidence Intervals, 1 proportion Z interval. We have 19 out of 32 with a 95% confidence level. So you see how it's exactly the same, 0.42 to 0.76, there's our p hat. Now, if you use your calculator on the AP exam without showing work, you are either graded 100% right or wrong, so same thing in my class. So if you use the calculator to find this confidence interval, you still have to do all this other stuff, and I would even recommend setting this up too. You don't have to, but you need to do everything, and I'll show you what the minimum is going to look like in class. Another thing we can do is determine the sample size. So a company has received complaints about its customer service. The managers intend to hire a consultant to carry out a survey of customers. Before contacting the consultant, the company's president wants some idea of the sample size that she will be required to pay for. One critical question is the degree of satisfaction with the company's customer service, measured on a 5-point scale. The president wants to estimate the proportion P of customers who are satisfied, that is, who would either choose satisfied or very satisfied, the two highest levels on the 5-point scale. She decides that she wants the estimate to be within 3%, so 0.03, at a 95% confidence level. How large of a sample is needed? So determine the sample size needed to estimate P within 0.03 with 95% confidence. So what we're going to do is we're going to set up an equation without n. We're going to solve for n. 0.03 is the margin of error, right? If you remember from a confidence interval, it's our point estimator plus or minus our margin of error. And our margin of error is the critical value times the standard deviation of the sampling distribution. So we know our margin of error needs to be 0.3, so 0.03 equals, remember our critical value at 95% confidence is 1.96. Our standard deviation of the sampling distribution is our p 1 minus p over square root of n. Now, we don't know what p is. So if we think about our sampling distribution, if our p is low, close to 0, we kind of hit this wall and we don't have quite as much error. If p is high, aka close to 1, you have the same thing on this side where it's kind of cut off. So the p with the greatest margin of error is going to be right here in the middle at 0.5. When we don't know what p is, we use 0.5 as a conservative estimate. So in our equation, we're going to use 0.5 for p. And we don't know what n is, but we can solve this now. Now, we could use algebra to solve this, or I don't care about your algebra skills, we could use the calculator to solve it, and I'll show you how to do that right now. You're going to go to Menu, Algebra, Solve, and this is where you type in the equation. Now I changed n to x because I want to solve for x, and when I use the solve feature, I just need to distinguish with a comma. I'm solving for the variable x, and it solves it for me. 1,067.11 people. Now, if again we're being conservative, so we would round it up to 1,068. So that's the ultra conservative estimate. We were conservative about our p, and we rounded up for an extra person.